great to be here at Buzzwords. Good afternoon to everyone. I want to get a sense for who you are before I start talking. Who in here sort of considers themselves a machine learning practitioner? Okay, a few of you. How about search or recommenders? Okay. Anyone work with data more generally? Most of us, right? Okay, awesome. So my goals in this talk are to give an overview of some of the themes in what I think is a really cool area of computer science, with a few representative examples of real systems and applications. I want to make connections between some fundamental programming language research topics and some of the kinds of things we talk about at Buzzwords, like search, recommenders, and machine learning. And I want to give you some ideas for how to take these techniques and use them to get more out of machine learning systems that happen to read or write programs. I do need to start with a disclaimer. I work for NVIDIA, but I don't speak for my employer. I'm here on my own time talking about something that I think is interesting, and these are just my opinions. The second disclaimer is that I have some background in programming language research, but program synthesis was not my area. It's a huge area. I'm trying to give a flavor for some key ideas and systems. My presentation might be idiosyncratic because it's what I thought was interesting and not necessarily what an expert would think was interesting. So let's start off. We're going to start off by defining all the noun phrases I had in the title. We're going to look at two of the key problems in program synthesis. How do we decide what a program that we're going to generate should do, and how do we decide whether or not it does it? And then how do we search the space of possible programs to find one that does the thing we want it to do. We'll look at a technique called programming by example, which has had a lot of real-world successes. We'll look at program synthesis techniques that allow us to take a specification, which can be everything from a formal specification to a bad or incomplete program, and turn it into a program, or if it's already a program, turn it into a better one. And then finally, we'll look at LLMs, because I think for most people, if you think about using a computer to generate a program for you, you're asking an LLM to do it in 2025. And I want to talk about how LLMs fit in with the topics that we're talking about in the rest of the talk and where we should go forward. So we'll start with defining those noun phrases. First off, do what I mean. I've not actually yelled this at a computer, I don't think, but I think I know people who have. It refers to a classic shell feature, predating Unix even, that aimed to automatically correct user typos and syntax errors based on some heuristics about what the author thought you were trying to do. And you can see similar functionality that's fortunately not automatic in commands like git and in package managers, where if you mistype a subcommand or a flag, they'll look at the edit distance to some flags that they know how to do or packages that exist and suggest alternatives. In program synthesis, we're also interested in user intent, but we're in general not trying to guess what someone means. Okay, next question, what is AI? And I got to keep an eye on the exit because I just asked what is AI in a technology conference talk in 2025. I think this is actually an interesting question though, right? People still don't agree on what AI means. I thought we'd have an understanding by now. But if you paid attention in the keynote this morning, you may have some idea about where I'm going. It was a nice setup for this slide, actually. AI means a lot of things. In my lifetime, I think the popular and business definition has been fairly constant. We're automating human-like reasoning in the service of economically meaningful human activities. But three technical definitions from my lifetime come to mind. The first is symbolic AI. It's deductive search on a database of facts and relations, often in Prolog or Lisp. The second one is inductive learning of rules from examples, the data mining, classical machine learning, things like linear models, things like tree models. And then finally, what a lot of people mean today, learning arbitrary functions on high-dimensional data with deep neural networks. And in each of these cases, we're searching something, right? In symbolic AI, we're searching a database or a graph to find answers to a query. We may need to guide this search so that it actually terminates or that it doesn't explore irrelevant parts of the graph. In machine learning, we're searching a large space of possible parameters, weights, biases, tree split points, and so on, and we want a way to evaluate whether or not one of these assignments is better than another, and we want to restrict our search space that we're more likely to encounter better assignments than worse ones. In program synthesis, we're searching a large space of possible programs. we need a way to determine whether or not a program is satisfactory. And again, we want to restrict our search space as much as possible. So here are some of the 3 fundamental questions that I think about in program synthesis. The first one is, what does it mean to have a specification for a program? And we'll see there are a lot of answers to this. The second one is, what is an acceptable program structure? Is that a syntax tree? Is that a program that just has some missing pieces? Is that a type signature, perhaps a really expressive type signature? It could be all of these. And then, once we have a bunch of candidate programs, how do we evaluate and rank these? Can we efficiently evaluate and search the entire space of possible programs? I think one thing that's interesting as a connection with information retrieval is there are a few kinds of questions that we ask in program synthesis and that we ask in areas related to program synthesis that are related to questions we think about in information retrieval. And one is, if a program synthesizer returns a program, do we know that it's correct? Right? And this is basically having, this is precision, right? Are all the retrieved programs relevant? The other side of that is, if there is an answer to a program synthesis problem, can we guarantee that we'll actually find it, right? And this is recall, right? Are we actually retrieving a relevant program? So I want to talk now about a few applications that I think are relevant to people who work with data, just to sort of get a feel for how these techniques are actually used in the real world. The first one is flash fill in Excel. How many people have used flash fill in Excel? Okay, I'm not an Excel user, but this is like a really cool feature. I almost want to become an Excel user just for this feature. The idea is that you give an example of how you want to extract a string from another cell, and it just will automatically complete it for you. And it does pretty well, right? It's usable in a lot of cases. And in this case, we have 3 examples, which I sort of reworked from the flash fill paper, which include generating acronyms from phrases, extracting components, in this case the day, from a date, and normalizing phone number formats to add a default area code to remove parentheses, and so on. A second application that I think is really interesting is Wrangler. Has anyone used Wrangler or Trifacta? Okay, this is a very cool system. It started as an academic project. It was commercialized as the Trifacta product, and it lets users interactively experiment with data transformations. It's essentially a program synthesizer for the space of possible ETL jobs, and it suggests transformations based on the data it sees and the user context. So here's a figure from their paper that shows the interface, and this is the kind of messy data set that I think everyone has bad dreams about, right? You have basically a CSV file with headers for subsets of the data set in individual rows. There's a variable just as sort of free text in one of those headers. No one wants to think about this, right? So what do? Well, they have some transformations that you can do. So they've automatically turned this data into rows. They've turned the top row to a header sort of automatically. And then there are these suggested transformations, which are templates. So you can click on these things and have it change what it thinks you should do, try them out, and if they don't work, you can undo them, or if they do work, you can export it as a script to run. And then the rest of the interface is an interactive display of the data set. So users can select things to guide a substring extraction. They can make changes that are reflected in transformations, and so on. And these bars at the top are estimates of data quality. So in the paper, they show how Wrangler more or less automates cleaning these kinds of messy data into a long, tidy data set where you have one observation for each number per state per year. And if you want to learn more, this QR code will take you to the paper. All right. The third application I want to talk about is inductive logic programming. I should ask, has anyone here used a system like Prolog? All right, got a few. So the basic idea is you have a database of facts, right? In Prolog or in inductive logic programming, these are relational clauses that encode observations about something of interest, right? In inductive logic programming, instead of defining rules, which you would do in Prolog, you also have examples of relationships involving the facts you have, both positive and negative examples. And the ILP system takes these and produces a hypothesized set of rules. It works backwards from the examples you gave and the facts you have to sort of infer lots of rules that may or may not do a good job of modeling the problem you care about. Now, in this simple hypothetical example, we're showing a database of a single kind of fact and a relation that's just a function of that fact. That's not super interesting, right? You could use logistic regression or a tree ensemble for this. The real power of ILP is that you're not limited to learning from fixed length vectors. You can learn from sort of arbitrary graphs and structures of data, and you can learn arbitrarily complicated rules, which is really interesting. Another thing is that a learned rule system is more likely to be interpretable sort of more or less directly than logistic regression coefficients or tree ensembles. That's not to say that those models aren't interpretable. It's just to say that you can look at rules and do that. And for an example of this, here's a link to a paper from the early 2000s, which is when inductive logic programming was really having a lot of success in bioinformatics and medical data analysis, showing inductive logic programming for cancer screening, basically inferring rules, taking those to domain experts and saying, does this fit with how you understand the world? And that's a very cool thing for a machine learning technique to do, or a program synthesis technique. And I guess I would argue that this is both, right? To show you something about the world that you'd need a domain expert for. Okay, so we're going to turn now to how program synthesis actually works, now that we've seen some examples. And two of the key programs of program synthesis really go hand in hand. How do we specify the intent behind a program? And how do we show that the program we've generated satisfies the intent that we specified, right? And there are a lot of examples of how we can do this. We'll see a few of them now. The first and oldest way to do this is with what are called Hoare triples. And it's from Tony Hoare in 1969. This technique, he popularized it. He didn't invent it, but it has his name. And it inspired a lot of other conventions in software engineering, like design by contract, if you've used the Eiffel language or similar languages that have sort of preconditions and postconditions for functions. The idea is that you have a program. Here we have just a very simple one-line program. And when you write your program, you also specify a precondition that must be true before the program executes, and you define a postcondition that will be true after the program executes. And the interesting thing about this system is that there's a whole formalism for taking these and propagating them through a larger program. So you could say, given that I have this precondition and this sequence of statements, I can generate a postcondition for each of them mechanically and use this to prove something interesting about my program. And in this very simple case, even if you just know that T1 is the maximum of X and Y, you know at least a couple of interesting things about T1 that might be useful somewhere else in your program. Another kind of programmer intent we can capture by just looking at sets of example inputs and outputs. These can be useful both for really inexpensive ad hoc testing and also for generating programs that satisfy these kinds of examples, as we'll see later. How many people have used property-based testing before, like Quick Check or a similar tool? Very cool, very cool. So we can, so checking the properties of results is another thing. Maybe you've done testing like this manually. Maybe you've used a tool like Quick Check to explore a large space of possible examples and see if certain properties that you want to be invariant are satisfied. But here are three other ways to specify what a reverse function should look like, right? We could say, does the reversed list have the same length as the original list? Does it contain the same elements but not in the same order as and then finally, most precisely, does it contain the exact same elements in the exact opposite order? Those are all ways we could specify programs. We could also have an inefficient program. What's wrong with this reverse implementation? Besides that it's like longer than it needs to be. So this is, I guess I should have asked if we have people who are comfortable reading Python before asking you to debug my code. The problem with this function is that because we're doing reverse recursively in this way, we're constructing a new list essentially for every element of this. So this is quadratic complexity, and it's wasting a lot of space. So we could use this as an input to a program synthesizer to say, hey, I want something that does the same thing as this program, but not as inefficiently, right? Another thing we could do is to specify intent is have an incomplete program. Any NumPy users or any Scala Breeze users? Do you have to look up slicing tricks all the time? I feel like I have to look up slicing tricks all the time. There is a slicing trick, a one-liner expression you can put in here to make a reverse copy of a Python list. I had to look it up. I never find myself having to do that. But if I know that there is some expression that could go there and I want to have a program find it for me, this is another kind of way to specify programmer intent. Finally, it's 2025. I have to sort of give another way to specify programmer intent, which is to have a natural language specification and have a language model generate that program for you. So the line between specification and validation can sometimes be blurry. Many of the techniques we just talked about could be used either to specify a program or validate that it meets a specification. But we're going to look now at a couple of techniques that are more firmly on the validation side, starting with model checking. The idea behind model checking is that we're going to encode a program and some invariants of interest in such a way that we can explore a very large space of possible program executions. So we're modeling the program and modeling the assertions we care about, and we're checking that model by exhaustively or maybe just extensively exploring that space of possible executions. If the model checker doesn't find any errors, it doesn't necessarily mean that the program is actually free of errors, because it may not be exhaustively exploring that space. But if it does find an error, it has a very useful property, which is that it will give us a counterexample. So if we've encoded these properties we care about, we have them basically encoded as a Boolean formula where we have this is the program and this is the properties. And we want to make sure that the thing we want to have true is not false, right? If the program and all the things we know about it are also true. And as an example, here is a C program that has a bug. I guess I'm not going to ask anyone to find the bug unless you really want to, but I'll give you a second to think about it. So this is a personalized hello world program. If you call, yes? Well, so 0 in C, yeah, that would not crash. And that would give you the name of the executable, though, at least on Unix. So this program will crash if you call it with no arguments, which is the problem. Yeah. And so we can use a model checker to encode this problem and say we care about array bounds checking. Let's see if we can encode that along with some details about how the program will be called. For example, some specialized knowledge that argc and the length of argv are going to be correlated, right? Or the same. So we'll encode this as logical formulas, and we'll try and get a counterexample that shows us why this is the bug in our program. So I just passed this to an off-the-shelf model checker, the C-bounded model checker, and I said, do some bounds checking, do some pointer checking, and if you fail to check the program, give me a counterexample. And as you see, it says, hey, we have a pointer outside the bounds of your array on the thing that I underlined earlier. So that's really nice. Being able to get a counterexample, as we'll see, can be a really useful feature when you're trying to explore a program space. The last thing I want to talk about is static analysis. I'm not doing static analysis justice on this slide. This actually was my research area. But it's a family of techniques to basically establish guarantees that programs have certain properties. And the difference with model checking, which is also a family of techniques to guarantee that programs have or do not have certain properties, is that with static analysis, if your analyzer says, this program doesn't have this problem, it definitely doesn't have that problem. But the static analyzer may reject a valid program because it has to make conservative assumptions to not allow any invalid programs to go through. So in general, you're going to use these two tools in combination. You're going to have a model checker and a static analyzer to catch more problems. So we have some ways to specify programmer intent. We have some ways to validate programs. Let's see how we can explore that space of programs. We have a language, we have some correctness criterion that reflects programmer intent. We want to search that space of possible programs. This was long considered to be an extraordinarily hard problem for practical applications because the space was so big. And to see why, I'm going to look at a real language. The real language is MIPS assembly language. MIPS is a RISC architecture that was historically important for workstations and gaming consoles. Some famous devices you might have heard of that use MIPS processors or the MIPS instruction set are SGI workstations, the Nintendo 64, and the PlayStation 2. So you may also know MIPS from a computer organization or compiler class that you took as an undergraduate because it has a really elegant and regular instruction set, which is why I'm using it as an example in this slide. We have 3 different kinds of instructions. We're not going to get into the details, but the blue and purple boxes encode the instructions themselves, and the other boxes encode operands of the instructions. So orange and green boxes are registers, either input or output registers, and magenta boxes are constant values. So with the first kind of instruction, we have roughly 27 million possible R-type instructions in the MIPS instruction set. For the second type of instruction, where we're loading an immediate value, we have a constant value, and we're doing something with it with registers, we have like 1.2 billion kinds of instructions. And then for the third, where we're jumping pretty much to a large part of our memory space, we have 134 million or so instructions. So if we look at all of those together, we have 32-bit word, right? So there are over 4 billion possible instructions, but only 1.37 billion of them are actual potential MIPS instructions. Whew, really trimmed down that search space. So I have a lot of trouble thinking about how vast this kind of space is, right? But if you have an 8-instruction MIPS program, there are roughly 10,000 times more valid 8-instruction MIPS programs than possible shufflings of a deck of French-style playing cards. We have anyone here who prefers bells, acorns, and leaves to clubs, spades, and diamonds? Okay, it is international conference, I guess. There are an order of magnitude more 4-instruction MIPS programs than there are shufflings of a 32-card scat deck, right? And there are around 100 times as many valid 9-instruction MIPS programs as there are atoms in the observable universe. I can't do anything interesting with 9 MIPS instructions. This architecture has a delay slot, right? Like I mean, for loads and for branches, you're not gonna get anything done in 9 instructions. If we could test a 9-instruction MIPS program in a single cycle on a 2 gigahertz processor, it would take 10 to the 72nd times the age of the universe to explore the whole space. So we're not going to do that. We need some way to bound the search space. And a very easy and effective way to do that is to only consider programs of up to a certain tree depth or up to a certain size. And here I'm not looking at MIPS assembly language anymore. I'm looking at a very simple language for string manipulation. We have two kinds of operations. We have taking a slice of a string, a substring, and we have concatenating 2 strings together. And the operands for these things are either strings that are supplied as input or they're constant values. Very, very simple language. And these 2 syntax trees both do the same thing. But if we look at the shortest programs first, we should prefer the one on the left, right? Because it's much shorter and it's also much clearer to a human reader. There are many other ways besides restricting our space to looking at the shortest programs first to bound this search space, and we'll learn about some more of them while discussing programming by example, which is what we're going to do right now. Programming by example is also called inductive program synthesis. This is the problem of I have a set of examples and I want to explore a space of possible programs to find a program that returns the correct result for all my examples. So in this case, I'm looking at a string extraction program. In the US, we have 2 kinds of postal codes. There's a general 5-digit one for identifying small towns or regions of larger cities, and there's a more precise 9-digit one that might be a street or a neighborhood or even just a building. And this example shows how we go for the 9-digit postal code for the field where my local football club plays to a 5-digit one. And there are many ways we could write a program to satisfy this example, right? I have 3 of them here, right? The easiest is probably the one on top, but it's least likely to generalize unless there are a lot of other buildings that we care about very close to the football pitch. The second easiest is just to take a static slice of the string, and I hope we wouldn't even be exploring the space anymore by the time we got to the third one. If we don't have a bounded search space, there are infinitely many ways to generate a 5-character substring, because we can just keep concatenating empty substrings together as long as we want, right? Fortunately, the techniques we discussed earlier for bounding the search space still apply. We can explore the shortest programs first, and there are more as well. We can also borrow ideas from machine learning and explore the space stochastically using MCMC, Monte Carlo T-search, or other techniques. One question with learning from examples is, what happens if you don't have many examples or any examples? Can you still learn from examples in that case? Well, one idea that can help you get more examples or help you learn examples is really analogous to something that a lot of programmers do while testing software, right? Say you're testing software, you run into a bug that wasn't caught by your test suite. You run into a bug in production. What's the first thing you do? You close the ticket probably, but the second thing you do is you write a test, right, that exposes the bug you just ran into. And this is a very similar technique for program synthesis. The idea is we generate a candidate program that returns correct results for our entire example set, and then we run it through a verifier with some property we care about. In this case, we want to say, hey, if you're giving me the postal code, the shorter postal code from a longer one, you should be returning something that was in the input. Right? I don't know how you got it, but you should be returning something in the input. And if we do this, we can then reject this spurious program and generate a new example from the counterexample that our verifier produced, which maybe the verifier started here and found that counterexample right away. So I want to do a case study now, and we're going to look at Flash Meta, which is the successor to Flash Fill in Excel, and we'll sort of dive in a little bit about how this works. So there are three really cool ideas in this system that I want to call out. And the first idea, I think for those of you who spent time thinking about neural networks, will be familiar. Because the idea is we start with the example and we work backwards using the semantics of the language. So we have a forward semantics for our language. What does this expression evaluate to? And we have a backwards semantics for the language. Given an expression that maybe has some variables in it and an output, how could we generate that, right? And so that means that we can constrain the part of the search space. So as a concrete example, if we were doing my extraction program earlier, we know that the output is a substring of the input. So we know that we don't need to consider any syntax tree that has a concatenation operation at the root, because it's just going to be wasting time to look at that part of the space. A second idea is something that there are echoes of all over in computer science, which is choose a more efficient representation. There's a representation of entire sets of programs called version space algebras. And it exploits redundancy so that you can operate on these entire sets of programs without enumerating them. So what we can say here is that if we have a program set that satisfies a particular example, and that the programs in that program set can solve that example, and we have another program set that can solve a different example, well, we can take the intersection of those two program sets, and if there is an intersection of those two program sets, that will be able to solve both the examples, which is a very cool feature. And there are other things you can enumerate these, you can rank them, you can do a Cartesian product with them, a lot of the sort of algebraic data manipulation operations you'd think you'd want. And the interesting thing about being able to do these things and having a ranking function is that you can actually learn a ranking function that chooses the best candidate program based both on how likely you think it is to generalize, or how likely the model thinks it is to generalize to examples beyond the ones provided, but also a ranking function that puts all the programs that fail at least one example below all the ones that pass all them. So I don't know if you're interested in learning to rank. Did you know that there was a learning to rank implementation in Excel? Pretty cool. So if you're interested in these techniques and want to see how we sort of do all this, I would recommend the Flash Meta paper as an excellent read. So now we're going to talk about how we can use program synthesis when our specification is a program that's not ideal, or when our specification is something we want to turn into a program more or less directly. And one example of this is if we have preconditions and postconditions and we have some holes that we want to fill in our program. This is not, including this for completeness. There are, sometimes you can fill in things because there are only a few things that fill it in. It's at least a way to restrict the search space, right? But this is not generally a practical technique. A technique that's surprisingly practical, though, is looking at a kind of invariant that I think many of you have probably used in programs, which is types, right? A very interesting property of types is that if you have a polymorphic type system, there are very few functions that can actually have certain type signatures. This first one, if you have a function that for any A, where A is a type, takes a value of type A and returns a value of type A, how many functions could that be? It's not a trick question. If you don't know the answer to this, it might be hard to come up with it. But I think the way you would sort of deduce what it is you'd say, well, what do I know about a value of type A if I don't know what A is? Nothing, right? I know that it's there. What can I do with a value that I don't know anything about? I can give it back to you, right? So this top function has to be the identity function. Does anyone recognize what this second function is? Yeah. It's map. Yeah, I mean, if you had someone who was trying to trick you, it could probably be something else, but this is almost certainly map, right? So types are also useful constraints on the program space we can explore, and more expressive type systems are used in theorem provers to actually generate correct specifications, correct behavior programs from more detailed specifications. So there's a classic example of algorithm replacement, like we sort of talked about with the reverse example earlier. This is a similarly inefficient Fibonacci function. We have 2 recursive calls. For each one, we're going to be computing a lot of redundant values. This is actually exponential in the argument in terms of complexity. We can look at a quick example of how this grows. This is, if we're doing the 5th Fibonacci number, this is what it looks like in terms of recursive calls. You've already thought of the 5th Fibonacci number while these slides are animating, right? That's bad, but if we want the 6th Fibonacci number, it's worse. And if we want the 7th Fibonacci number, we're running out of slide, right? So if we go back to 1969, which was a great year for formal methods, there's a classic paper by Rod Burstall and John Darlington that shows how you can mechanically transform programs to more efficient ones. And they have a set of rules. The interesting thing about the rules is some of these rules expand the program and some of them contract the program. You can inline functions, you can extract functions, you can introduce new functions. Basically what they do, though, is they use these rules to show that you can turn this into a function that returns a tuple and operates in linear time rather than exponential time. So we essentially, with this pseudocode notation, we go from something like this to something where we have a helper function that returns a tuple and only has to compute each Fibonacci number once. That's sort of a classic example. This, for a long time, was something that people did by hand. There are definitely tools that can do some of this stuff more automatically today. Another example of improving programs is the idea of super optimization. If you've worked with compilers or computer architecture, you may have heard of a peephole optimization. Oftentimes, compilers generate suboptimal machine code because they're translating small parts of the program independently and then concatenating the results together. So you might have a program like this that has some redundancies in it. In this case, we have x equals y, z equals x plus x equals y equals x equals a. Right? We're never really using the value of x here, so we can eliminate that. And then if we see that we don't use the value of x before we write to x again, we can rewrite that z equals x plus x and replace it, and then keep 2 instructions instead of 5. So this is sort of a tricky thing because, again, you have a bunch of rewrite rules, some of which will expand your program so that you can contract it in a different way later. It's not obvious how to follow these rules. And it's very computationally expensive. It's a combinatorial search problem. So compilers historically have only done this on like tight inner loops. They haven't used this technique often. Bonsall and Aiken in 2006 introduced a clever technique in the domain of super optimization, which basically generates optimal rewritings for a database of target instruction sequences offline, translates sequences to a canonical form using a table of sequence fingerprints to avoid recomputing those canonical forms, and then uses simulated execution and a model checker to show equivalence between two sequences in the database. You can say, hey, I have a sequence that has this hash, find me the optimal version of that sequence. So we have basically a training phase, we have an online sort of inference phase. This is a lot like a machine learning system. And the really cool thing about this is that all of the hard work it does is essentially offline or saved for later. This is a system that gets better the more you use it, and that's pretty inexpensive the first time you use it, even though it's solving a very hard problem. I'd recommend looking at the paper. The link is there. So with LLMs, we have some sort of interesting similarities and differences. Given programmer intent, we want to produce a working program. But LLMs are operating on tokens, not on syntax trees. So that means that we may not even be getting a syntactically valid program, let alone a program that makes sense. This Python code snippet turns into 22 tokens, which I've highlighted here. And we can't guarantee that the program is going to be syntactically valid, although LLMs do a pretty good job, and many of them use some kind of constrained decoding to make it more likely. I want to ask some sort of more philosophical questions, like what can LLMs learn from program synthesis and verification techniques? Should we be specifying verifiers for our LLM-generated code? Should we have counterexample generation for our LLM programs? Given a library or language, can we enumerate or sample interesting programs to generate a training corpus? I also want to ask what the programming language community can learn from LLMs. Historically, using provers, model checkers, all kinds of software quality tools has a really high barrier to entry. But this is really important because we depend on software for a lot of things. So I'm wondering if LLMs can make these more accessible to everyday programmers for everyday programming. I have a philosophical question that I'll do very quickly, and then I'll close. And the philosophical question is, what does it mean to solve a problem? This is the classic Towers of Hanoi puzzle. You move disks from one peg to another, you can only move one disk at a time, and you can't put a larger disk on a smaller one. Has anyone read anything lately about the Towers of Hanoi puzzle? It's been in the news. So there was a fascinating paper from Apple Research recently that everyone on the internet seemed like they were talking about for about a week. And the illusion of thinking. It aims to show that reasoning models, which are LLMs that think out loud to produce better results, aren't actually doing what anyone would consider reasoning. I think it's super important to think about what it means to reason as a human, what an LLM is doing when it has a chain of thought, and why it works and why it doesn't, and what it means for machines to be useful even if they aren't actually thinking. But the thing that stood out to me is that they use the Towers of Hanoi as one of these puzzles to demonstrate how reasoning models break down. And these charts show that as the number of disks increases, the correctness drops precipitously. I think this is an interesting experiment, but I had a couple of tongue-in-cheek reactions almost instantly, which is that if you asked me to write out the moves for a 15 or 20 disk Towers of Hanoi puzzle, I would ask what I'd done to offend you, right? I'd be more likely to write a program and show you the output, which is also what I'd ask the LLM to do. So I turned around and asked an LLM to make me a Python program that would make an MPEG-4 animation of the Towers of Hanoi program with 5 disks. And I ran it, and it crashed. But I gave it a single sentence of feedback mentioning the error, and then I had a working program, which I'm going to show you right now. Unlike me moving disks around by hand on a slide and mangling keyframes, it didn't accidentally reorder anything and put 2 disks in the same place at the same time. So there's an interesting philosophical question at the intersection of AI and program synthesis. To what extent should we connect LLMs to other tools, and to what extent should we address the apparent limitations of LLMs through post-training? I have a bunch of links to projects to try and things to read in my slide deck. I'm not going to go through them now. I'll let you read them offline. But I do want to just sort of conclude with the sort of main themes that I think we've talked about today. Search, constraint solving, and optimization are really, really useful, whether you're exploring parameter spaces, documents, or program spaces. An idea that was interesting but impractical 50 years ago, like, say, artificial neural networks or program synthesis, might just be feasible and useful today. I think it's fun to think about what techniques are going to be feasible and useful 10 years from now that we don't think are practical, and what might have to change to make that so. Finally, language models are surprisingly good at generating code today. Being able to tune and constrain their explorations could make them even better at it. It's always a pleasure to be at Buzzwords. I've enjoyed getting a chance to show you some connections between some cool topics, and am really happy to chat at any point during the conference if you want to discuss this further, but I'd love it if you keep in touch.